Start recording. Almost forgot. Yeah. You put the time domain signal here, right? And you multiply it by e to the negative st, and you integrate it with respect to time, going from 0 negative to infinity. Now, 0 negative means just before time 0. So the importance of this is that sometimes there is a function x that exists only at time 0. For example, the delta function, this function exists only at time 0. So using this notation means that we are including the delta into the integration, okay? But if we write it as just 0, then it would be problematic when we are dealing with the delta function, because that function exists only at time 0. So that's why we have to include the negative symbol right there. That's one thing. Another thing is the variable s here is usually a complex variable. So that means that the value of s is a complex number, okay, where we denote the sigma here as the real part of s and the omega here as the imaginary part of s. Right. So that is the Laplace transform definition. So it's kind of like it transforms. This integral transforms from the time domain xt to the s domain xs. And so we don't have to deal with xt anymore. So we're going to be dealing with xs. And that is hopefully a lot easier. Okay, and we are using this notation, the capital L here, to mean the Laplace transform operator. We put xt here inside the L. Okay, so that means that we are doing the Laplace transform on xt to get xs. And we are also using this notation to mean that these two are a Laplace transform pair. So once we know xt, we know xs, and conversely, if we know xs, we can uniquely identify xt. Okay, so they are a pair. They are a pair. Right? They belong to each other, no one else. And we also use this notation, L to the negative 1, to mean the inverse Laplace transform of xs. So if you put xs into here, we're going to get xt out. Now, the first property of the Laplace transform is probably the most important property, and that is linearity. Linearity tells us that if we do the Laplace transform of a linear combination between two signals, the result would be just the linear combination of the Laplace transform of those signals. So in other words, you can simply take the operator L inside of the parentheses. Okay, you take L into x and you take L to y to get this. Okay. Oh, and A and B there are constants which can be complex numbers. So A and B can be complex numbers. And also true with the inverse Laplace transform. So it means that the inverse Laplace transform of the combination is going to be equal to the combination of the inverse Laplace transform. And we use this property to find the Laplace transform of a sinusoidal, which starts at time 0. And we found, using the Euler identity, we found that the Laplace transform cosine is given by this. So you see here, we are transforming from the time domain signal into the S domain signal. So every time we see this, okay, every time we see this, we know that xt would be a cosine signal with this number as the angular frequency, okay, starting with time 0. On the other hand, the Laplace transform of sine is this guy. Okay, they are quite similar, right? The denominator is similar, it's exactly the same, except for the numerator. the numerator of cosine is s, but the numerator of sine is the angular frequency omega 0. Now another important property is time shift, which goes like this. We are shifting, notice here that we're shifting the entire signal. And after we shift it, we start at time 0 here. So we're going to take a Laplace transform of the shifted version starting at time 0. This means starts at time 0. And the result would be equivalent to multiplying the Laplace transform of x by the exponential here. Okay, where t0 here, t0 is the time that we've shifted. Okay, right. The next one is, I don't remember what the next one is. Let me take a look. The next one is time differentiation. Okay, next one is property number 3. By the way, we will not be proving these properties. Okay, we don't have enough time to prove these properties. We will find the Laplace transform of the n times derivative of x. So this means, this symbol, this notation means that we take the n times derivative of x and take the Laplace transform of the result. Okay? We first take the n times derivative of x and then take the Laplace transform of the result. And after we've taken the Laplace transform, it's just equal to s to the n times the Laplace transform of x itself, okay, and minus x to the n minus 1 x at time 0 negative minus s to the n minus 2 x 1 0 negative minus all the way to s x to the n minus 2 0 negative, and minus the last term is x to the n minus 1 0 negative. Okay, but you don't, I think you don't have to remember this, because I'll tell you, okay, I'll give you this formula in the exam paper, so you don't have to remember this. Now, so what are these notations? The first notation is here, x at time 0 negative. So what does it mean? It means, this means the value of x just before time 0. Okay? The value of x just before time 0. For example, if x is delta, then this is going to be 0. Okay, because delta starts at time 0, right? But this is just before time 0. So if x is delta, this term is going to be 0. So this means that the value of x just before time 0. Now, what does this notation mean? What is the one inside the parenthesis mean? This notation means that we are going to take the derivative of x with respect to time. And after taking the derivative with respect to time, we plot t as 0 negative. Okay, so you get this. We take the first derivative of x with respect to time, and once we do that, it will be a function of time, right? And then we plug in time equal to 0 negative into the result. The result of this is this guy. And we multiply it by s to the n minus 2. Okay. Now, what is this term? What is this term? This term means we take the n minus 2 times derivative of x with respect to time, and then plug t equal to 0 negative to the result. So this is what it means here. Right. For example, if the inside parenthesis is 2, then we're going to take the second derivative of x and plug in the value of t equal to 0 negative into the result. Okay, now special case, for n equal to 1, we have Laplace transform of dx by dt, right? If x is equal to 1, then we're going to have s xs, okay, minus x at time 0 negative. This is the special case when n is equal to 1. We will have only 2 terms, right? Because 1 minus 1 is 0. It means that we are doing 0 derivative. So 0 derivative means that we are not doing derivative at all. So we get this. Now, what if n is equal to 2? When n is equal to 2, the Laplace transform of the second order derivative of x with respect to time is s to the second xs minus s x at 0 negative and minus x of 1 0 negative. This is the second order derivative and taking the Laplace transform. So this means, this guy means we take the first derivative of x, right? And then plug in t equal to 0 negative to the result. Okay. Now let's do some example. Consider the following differential equation. Dy by dt plus yt equal to ut. Where y at time 0 negative equal to 0. Okay, we want to find yt. In other words, we would like to solve this differential equation given this initial condition. Right. Now we'll be using Laplace transforms to solve this differential equation. In other words, we're referring to this box. Sorry. Yeah. We're going to be referring to this box. Now, this is the problem to be solved. The differential equation that I just wrote down was the problem to be solved. The next step is to determine the Laplace transform of that differential equation. And we'll be working on the s domain instead of the time domain. And once we've got the result, which is ys, we will be using the inverse Laplace transform to get yt back. So this is a step that we'll be doing. Okay, so the first step is to take the Laplace transform of this differential equation to transform from the time domain to the s domain. So let's do it. Now, we multiply each side we multiply both sides by e to the negative t. Okay, we start this step multiplying both sides by e to the negative st. Okay, once we do that, the left hand side would be dy by dt e to the negative st plus yt e to the negative st equal to ut e to the negative st, right? And then we integrate it from 0 negative to infinity. All right. When we do that, we're going to have 0 negative infinity dy by dt e to the negative st dt. That is the first term. All right. And the second term would be integrating from 0 negative to infinity yt e to the negative st dt, right? And on the right hand side, we have integrating from 0 negative to infinity ut e to the negative st dt. Now let's look at each term. Now let's start with this one. This one's the easiest. No, sorry. This one's the easiest. So what do you think of this one? This is the exact definition of the Laplace transform of y, right? So this is a Laplace transform of y. So if you take the integral, if you take the integration, we see that this is just ys. Right? This is just ys. Now what is this? The right-hand integration. The right-hand integral. What is this equal to? So we recognize that the right term, the term on the right-hand side, is the Laplace transform of ut, right? This is the Laplace transform of ut. What is the Laplace transform of ut, if you remember? That would be 1 over s. So it is one, the right-hand side is 1 over s. Now, probably the most difficult one is this guy. So what is this guy? Do you recognize this guy? Is this one? Okay, this is the Laplace transform of the first derivative of x over t. Right? So this would be the Laplace transform of dy by dt, which we know from this property. This is the case when n is equal to 1. Laplace transform dy by dt would be s ys minus y0 negative. So we plug it in as s ys minus y0 negative. Now we have all the ingredients, right? So we rewrite this equation in the s domain now. So this equation in the s domain becomes s ys minus y0 negative, okay, plus ys equal to 1 over s. Okay, now we are in the s domain. We have stepped fully in the s domain. So the next thing we would like to do is to rearrange this so that the left hand side is ys and the right hand side is a function of s. So let's do that. But first we have to plug in. No, not yet. So rearrange it. We have ys s plus 1 equal to 1 over s plus y0 negative. Right? And so ys equal to 1 over s times s plus 1 plus y0 negative over s plus 1. Now we have arrived at the ys. We have determined ys. So the next thing to do is to figure out what y0 negative means. The question tells us that this value is 0, right? This is from the question here. This is the initial condition of the differential equation, which is 0. So we plug in this as 0. Okay. Once we do that, once we know it is equal to 0, then ys would be 1 over s plus times s plus 1 here. But we don't recognize this. Not yet. We still have to have some work to do because this is not something we've seen before. So we have to rearrange it so that it is consistent with something that we have in hand. So we have 1 plus s plus s plus 1. We are decomposing. In other words, we're doing the decomposition of that function into two terms. Okay, and this would be 1 and minus 1. Now, how did I come up with 1 and minus 1 here? How did I get these numbers? Okay, we'll deal with this later. But for now, just trust me that this is 1 and that is minus 1. So that if you add them up, you're gonna get this. Just trust me on this one. I'll tell you later how to find these numbers. Now, so here we have two terms, 1 over s and minus 1 over s plus 1. And we recognize this already because the time domain for this is just ut, right? This is ut. If you take the inverse Laplace transform, this is going to be ut. And this is going to be exponential, right? So we know that the inverse Laplace transform of this is what? Is ut. The first term is ut, and the second term is e to the negative t ut. Okay? And this is just yt, right? Yt, right? So the answer to this the solution to this differential equation is 1 minus e to the negative t ut. That's it. Right? Okay. If I think we should probably go back to our diagram here. So what we did was, again, we were given this problem, which is typically in the time domain, right? For example, in the last example, we were given a differential equation in the time domain. And then we did the Laplace transform on that differential equation to transform from the time domain into the S domain, right? And then we solve the algebraic equation in the S domain, as you have seen already. And then we did the inverse Laplace transform of ys into yt. And finally, we get yt, which is the problem solved. Okay. So these are the steps that we took. Now, if we don't know, if we didn't know Laplace transforms, then we have to solve the problem in the time domain. we'd have to solve the differential equation in the time domain, which we could have done, but we opted not to do that. Okay, we chose not to solve in the time domain, but we instead chose to solve it in the S domain, which should be a lot easier. Okay. Now, so this is what's going on in the last example. Now, I hope everybody remember circuit theory. I'm gonna tell you a trick about how to solve circuits. Okay? You have this VT, V0T, and then we have a resistor R, and then we have a capacitor C. I'm not sure if you have seen this trick before, but let me tell you. Let me the one to tell you. I'm not sure if I'm the first one or not. What we would like to do is we would like to find the voltage across the capacitor here. Okay, given V0. So this is what we would like to do. So the trick is to convert V0T to V0S. We want to work in the S domain instead of the time domain. And if we see a resistance R, we convert it to R. If we see the capacitance C, we convert it to 1 over SC. So that is the trick. Now, if we see L, we convert it to SL. So in this case, that circuit in the problem is in the time domain. So we have to convert it into an S domain, which will be V0S, and then R, and then C, which is 1 over SC. Okay? And then the output is VCS. Now this circuit is in the S domain. And then we will use these values as resistances. So if you would like to find the voltage across this guy, right? We're just going to do voltage divider. So by voltage divider, we have Vc of S equal to 1 over Sc over R plus 1 over Sc times V0S, right? This is by voltage divider. I hope everybody remember it. So it is 1 over 1 plus R SRC. Oops, sorry. 1 plus SRC V0S. Okay. Now, to solve this, let's assume that the input voltage is a unit step signal. Okay. Then V0S would be 1 over S, right? And so when the input signal is unit step, the output signal in the S domain would be 1 over S times S1 plus SRC. Right? And then we can decompose it into two terms, as we've done previously. So the first term is S, the second term is 1 plus SRC. Actually, I should write it down like this. Sorry. Okay. These two are the same. These two are the same. And then I have one here, and I have -1 here. Yeah. Okay. And so the voltage across the capacitor in the time domain, we recognize that the first term is ut, right? And the second term is minus e to the negative 1 over RC TUT. Okay, so we plug those in, we get ut minus e to the negative t over RC ut. So that is equal to 1 minus e to the negative t over RC ut. Here. So this is the trick that I used when I was in undergraduate study, when I was yourself a while back. I was usually given circuits like this, and I was asked to solve for the output signal in the time domain. So what I did was I replaced everything. Okay, I replaced the resistor R with the same R. I replaced resistance C, capacitance C with 1 over SC. And then replaced inductance L with SL. So I rearrange the circuit into the S domain like this, and then I solve the circuit using typical method, right? For example, I can use KVL, I can use KCL, or I can use a voltage divider. So when I do that, I get the output potential in the S domain like this, and then I convert it by transforming it back into the time domain using the inverse Laplace transform, and I get the output in the time domain, which is what I was looking for. So the problem is a lot easier when you work in the S domain. This is just another example. Okay? And you can use this method to apply to every circuit that you want. And of course, you have to be able to find the inverse Laplace transform. And the next property is time integration, which is the the fourth property, time integration. Time integration states that if you take the Laplace transform of the integral taken from negative infinity to t, x of tau, d tau. Okay, we've seen this integral a lot, right? Before midterm. We've seen this integral a lot, so we should be familiar with it by now. So the result would be the Laplace transform of x, divided by s. This is called the time integration property. Okay, now let's do some example. Okay, let R equal to TUT. Now we're considering this signal, which is called a ramp signal, the unit ramp signal. So the unit ramp signal is a signal that increases with time linearly with a gradient equal to 1. So this is the shape of the unit ramp signal. It is 0 until time 0 when it increases uniformly with time. So this is the unit ramp signal. Okay, this is the graph of the unit ramp signal. We would like to find the Laplace transform of it. We would like to find the Laplace transform of this. Now, if you do it directly, okay, if you do the direct method, then the Laplace transform of RT would have to be integral from 0 negative to infinity and TUT e to the negative st dt, right? In the direct method, this should have to be equal to 0 to infinity t e to the negative st dt, right? Can you integrate this? Of course you can, right? You have to use integration by parts, right? Or you could. There's also a trick to do this integration, but we're gonna stop right here. Okay, you could do this integrating by parts. To get the result that we want. Now another method is to use the property in the time integration property. Okay, we know that we notice that RT is just the integral from negative infinity to t of ut dt, right? You recognize this? If we integrate the unit step signal, we're gonna get the ramp signal, right? In other words, if you differentiate the ramp signal, you're gonna get the unit step signal, right? Because the ramp signal has the unity slope. The slope of the ramp signal is always 1. Okay, so if you take the derivative of r, you're gonna get 1 all the way, right? 1, because the slope is always 1. So we know the derivative, the 1 here is just the ut, right? And because the derivative of r is u, so I'm sorry, the derivative of r is the integration of u. So u is the derivative of r, so r is just equal to the integral of u, going from negative infinity to t. This should be d tau, sorry. Tau. D tau. Okay. So by the integration property, the Laplace transform of r is just the Laplace transform integral from negative infinity to t u tau d tau. Okay, and that is equal to the Laplace transform of u divided by s, and that is 1 over s squared. So the Laplace transform pair of the unit ramp is just 1 over s squared. I should say TUT. TUT. All right. And we may take a note that if you take the Laplace transform of t to the nut here, okay, we take the n power of t, right? T to the n times ut. You will find using the time integration as well that it is the Laplace transform of it is equal to n factorial over s to the n plus 1. Why is that so? You can prove it. It's not that difficult, right? It's quite straightforward to do. But if you don't want to prove it, you just remember the formula here. Okay, the next one that I would like to talk about is initial value and final values, which is the number 5, right? Number 5, the initial and final value theorem. This is another property of Laplace transformation. Uh, First, the initial value, which is x 0 plus. Now, what do I mean by x 0 plus? X 0 plus means the value of the signal x just after time 0. Just after time 0. We're not including time 0, but we start at time just right after time 0. This is what it means by this notation. The value of xt just after time 0. We can find it using xs, right? And that is limit s goes to infinity as xs. This is the initial value. This is the initial value. Now, as for the final value, which is x at infinity, right? This notation stands for limit of xt when t goes to infinity, and that is equal to limit of xss when s goes to 0. This is called the final value. This is the final value theorem. Now, the initial value theorem is not that hard, it's not that difficult, but the final value theorem is a little tricky. Okay? In order for this equation to be true, this limit has to exist. Xt has to converge into something. If xt doesn't converge, then we cannot use the final value theorem. For example, if xt is cosine, cosine doesn't converge, right? Because cosine is oscillating from negative 1 to 1, right? All the way. It doesn't converge. So for cosine, we cannot use this final value theorem. So to be able to use the final value theorem, xt has to converge. The steady state of xt has to exist. That has to exist a number. So note the final value theorem is applicable only if x infinity exists. If it doesn't exist, then we cannot use the final value theorem. It becomes invalid. Now let's look at an example. So let's consider this signal xs, which is s over s squared plus 2s plus 1. Now we are given this signal in the s domain, which is xs equal to s over s squared plus 2s plus 1. Now the question is, we want to find the final value as well as the initial initial value. We want to find these two numbers. Okay. Now from this theorem, we know that the initial value is the limit when s goes to infinity sxs, right? Okay. Then we can just plug in xs into this limit, right? So we have limit s goes to infinity, okay, and then s squared over s squared plus 2s plus 1, right? And this is equal to the limit when s goes to infinity. We divide both the numerator and denominator by s squared. So we have 1 over 1 plus 2 over s plus 1 over s squared. And when s goes to infinity, right? This term goes to 0. This was this 1. So we are left with 1 over 1. And that is going to be 1. So this is 1. So the initial value of the signal is 1. Just right after time 0. Now, as for the final value, and it is s squared over s squared plus 2s plus 1. You see, the numerator goes to 0, right? While the denominator goes to 1. So the limit of this is 0. Okay? All right. If you have questions, please raise your hand so that I know, or you can ask me right away. Now the next property, which one is it? The sixth one, right? The sixth one. The sixth property is called time convolution. Now, this is probably the second most important property next to linearity. Okay, so you should definitely pay attention to this one. Okay, it says here. It says that we remember time convolution, right? Convolution integral. Recall this. If we do xt convolution with ht, right? This is just the integration from negative infinity to infinity. Remember it? Do you recall it? X tau, right? Then ht minus tau, d tau. You should be able to remember this in your dreams. Okay. When you dream about this integral. Right? When you wake up with this integral. And when you eat with this integral. Okay. Eat it. This is how important. Now, the good news is this. When we did chapter 2, right, we had to do this convolution, right? The good news is that we don't need to do all this integral. Okay, we could have done it in the S domain, and in the S domain, it is a lot easier. So when we did convolution in chapter 2, I was actually fooling you into doing it. Okay, actually, you should do it. You should be able to do it. But there is another method which is a lot easier than doing the convolution integral, which is in the S domain. It's a lot easier. It goes like this. If we take the Laplace transform of xt convolved with ht, right? The result of the Laplace transform would be as if we're doing xs multiplied by hs. These two are equivalent. These two are equal. So what is the importance of this? Why is it important? Why does it make our life easier? Take a look at this example. In other words, the Laplace transform of convolution is equal to the product of the Laplace transform. Okay? In time domain, this is convolution, right? In the S domain, it is just the product. It is just the multiplication. So we have converted from integral into algebraic manipulation. Right? Instead of having to do integration, right? We can just multiply and add together, and that's it. So let us look at this example. Remember how our lives was miserable when we did this. Let x equal to e to the negative t ut, convolution convolved with ut, right? Actually, we want to find this. We want to find the convolution, the time convolution between exponential here with unit step signal. Now, if we didn't know Laplace transform, if we were still in chapter 2, so if we were still in chapter 2, then you would have to do this integral. Okay, which is not nice, right? Which is not nice. This is devil. Okay, this is devil. But now we know this property of the Laplace transform. So let's use this property. Let's use this method in order to find xt. So here, sorry, I have to go up again. Now, we have this problem. We would like to find the convolution between those two functions, right? We have this problem. So we would like to transform them, the both functions there, into the S domain using the Laplace transform, and then we do these algebraic equations to have xs, and then we inverse Laplace transform it back into xt. So we're gonna again follow these steps. Okay. Here, this is a problem to be solved in the time domain. So the first step is to convert it into S domain, right? So we know that the Laplace transform of e to the negative t ut, this is what we know. It is equal to 1 over s plus 1, right? Whereas the Laplace transform of ut is 1 over s. This is what we know so far. So that means that in the S domain, the signal x in the S domain, which is the Laplace transform of e to the negative t ut, right? Convolved with ut. Okay? And using this property, right? Using this property, we have two functions convolved together. The first being e to the negative t ut, the second being ut, right? And using that property, the property right there in the top of the page, it is equal to the Laplace of e to the negative t ut. Now, multiplied by the Laplace transform of ut. Okay, this is from the convolution property. Okay, but then the Laplace transform of e to the negative t ut is just 1 over s plus 1. So we have 1 over s plus 1, and the Laplace transform of ut is 1 over s, right? Okay, and then we have this is equal to 1 over s minus 1 over s plus 1. And now We can find the inverse Laplace transform already. Okay, because this guy is just ut, right? This guy is ut, whereas this guy is e to the negative t ut, right? So we know that xt is ut minus e to the negative t ut, or 1 minus e to the negative t ut. That's it. Easier? Is it easier than the convolution integral? It is a lot easier, right? We don't have, here, notice here, I didn't have to do any integral at all. Okay, but I think the most difficult step would be figure out what this is equal to. Okay, what is this equal to? Because we cannot do the inverse Laplace transform of this whole thing, right? We have to decompose it into some things that we can find in the inverse Laplace transform. So this is probably the most difficult step, the inequality here, which we will figure out later. Okay, we will spend some time on this decomposition. But for now, just trust me. Okay. Sorry. Any question? So let's do another one. Can you do this in 1 minute? I'll give you 1 minute to figure this one out. Let's try doing it in 1 minute. Can you do it? Let's give it a try. I remember the first lecture a while back. It was very crowded, like, right? Almost no seats available. But now, less people will show after the midterm. The final will be more difficult than the midterm. The midterm is probably the easiest exam. I mean, I'm not talking about the exam itself. I'm talking about the content of the material. The content, of course, Fourier series, Fourier transforms are harder than chapters 1 and 2. Okay, because you have to deal with complex numbers in Fourier series and Fourier transforms. Okay, right? Can you do it? Did you come up with the answer? So we are gonna take our usual steps, right? By convert it into S domain, by recognizing the Laplace transform of t to the nut, right? This is, I told you earlier, this is equal to what? Don't remember. To n factorial, right? Divided by s to the n plus 1. Okay? Whereas the Laplace transform ut is 1 over s. Okay? So we know from the convolution property that xs is n factorial divided by s to the n plus 1 times 1 over s, right? This is straightforward. So how do you go from here to xt? What's your opinion? Do you have any opinion to go from here to xt? Can you take the inverse Laplace transform out of this? Yeah, all right. So if we multiply them, right, it would be n factorial divided by s to the n plus 2 right? So the question, my question to you that is this equal to t to the n plus one ut? Is it equal to t to the n? Are they equal? After all, right? After all, we know that these two are equal, right? Sorry, this is n plus two, right? N plus two. After all, we know that these two are equal. So it is natural to think that these two are equal, right? See, this is n, right? And this is n plus 1. But this is n plus 1, so this should be n plus 2, right? And that is true. But if you look closely, you see this is n. It's consistent with n here. So if this is n plus 1, this should go with n plus 1, right? But we only have n, so what should we do? So we should do this, right? In order to make it n plus 1, we multiply by n plus 1. Okay? Right? And then the numerator would be n plus 1 factorial, right? Divided by n plus 1 is to the n plus 2, right? And then this guy, right? Now, this is t to the n plus 1 ut already. So this is, you can use the inverse Laplace transform here now. So xt, oops. So xt would be t to the n plus 1 over n plus 1 times ut. That's it. Okay? Easier than doing the convolution integral. That's why I have to teach you. That's why I have to teach you convolution integral first, right? Before teaching you this, because if you knew this, if you had known this before convolution integral, then you have done this method. The next property, I think it is number 7. Time periodicity. Oh, before talking about this, let me say something about refer to. Let's go back to the LTI systems. Okay, recall LTI systems. Okay, if you have an LTI system, this is an LTI system, right? The impulse response of which is ht. So let's suppose that ht is given. Now we're giving this system, we're giving the input xt to this system, right? And we measure the output yt out of this system. Okay? Then we know that the zero state response is yt equal to xt, right? And time convolution with ht. Now, what do I mean by zero state response? If you remember, it is the output of the system due to the input only. Okay, with with initial state assumed to be 0. No, the system doesn't have any initial states at all. The output signal is only due to the input signal, not the initial state. No initial states involved, just the input signal that gives you the output signal. So that is what a zero state response means. So because we know that yt is the convolution integral between xt and ht, right? We could take the Laplace transform on both sides. So we have y in the S domain, and we know that the Laplace transform of the convolution integral is equal to the product of the Laplace transform. So this is equal to h of s times xs, where we have to find that h of s is defined as the Laplace transform ht of the impulse response. Okay. Actually, this function is quite important. This function is quite important, and it has a name. Okay, and its name is the transfer function. The transfer function. Of the system. This is called the transfer function. It is quite important. And this equation tells us that if we know the transfer function of the system, then we could be able to find the output given any input to the system. Okay, that's what it means. So let's do an example. An LTI system has the zero state response given by y equal to 1 minus e to the negative t ut, right? When the input is ut. Now, the question is, we want to find the impulse response. Okay, the question tells us that when the input signal is the unit step signal is applied to a certain LTI system, that LTI system will give the output as this function e to 1 minus e to the negative t times ut. Given this information, can you find the impulse response of the system? Now, we could have differentiated. We could have taken the time derivative of yt, right, to get ht, but we will do it differently. We will do it using the Laplace transform. We will try to work it in the S domain. So to work it in the S domain, the strategy would be to take the Laplace transform of yt to get ys, and Laplace transform of ut, right? And then we have ys and xs. From ys and xs, we have this, right? We have this. The question actually tells us that these two functions. Once we know these two functions, we'll be able to calculate hs, right? And once we know hs, we will be able to find ht by taking the inverse Laplace transform. So in other words, we'll be following the boxes, the diagram again. We have a problem in the time domain. We convert it into the S domain. We work everything in the S domain to get the solution in the S domain, and then we convert it back to the time domain to get the solution. Yet again. Okay, so the first step would be to take the Laplace transform of y, right? We have yt, ys is the Laplace transform of yt, right? Which is the Laplace transform of ut minus e to the negative t ut. Okay, and from linearity, right? This is the Laplace transform of ut minus the Laplace transform of e to the negative t ut. This is from linearity. And this is Laplace transform ut is what? Yeah. When you dream of the Laplace transform ut, okay? It should be in your dream. So it is equal to 1 over s, right? Close your eyes and you should know it. And minus the Laplace transform e to the negative t ut is 1 over s plus 1. Okay? We've been over this, so I'm not going to talk about it again. Now, so this is ys. So this is s times s plus 1, and the numerator is 1. Okay? Now, what about x? X is the Laplace transform of ut, right? Because we know the question tells us that the input is the unit step signal, right? So in the S domain, it's just the Laplace transform ut, which we know is 1 over s. Okay, it is 1 over s. So since y is equal to h times x in the S domain, it follows that the transfer function of the system's y over x, right? That is a transfer function. Okay, you just divide x across to the left to get h. But y is 1 over s times s plus 1, and x is 1 over s, right? So if you divide them, you get 1 over s plus 1. So now we have our solution, but it is still in the S domain, right? So the final step would be taking the inverse Laplace transform to convert it into the time domain function. So ht this is what we are asked for, right? Is the inverse Laplace transform of 1 over s plus 1, which we know is equal to e to the negative t ut. That's it. Okay. Another example. Now, let's get back to our circuit again. We have a resistor, right? But now we have an inductor as well, okay? And we have a capacitor. Let's make it VIT, right? And this is VCT. Okay, we want to find the transfer function of this circuit. Let's call this ratio as the transfer function, which is the output in the S domain divided by the signal, the input signal in the S domain. So can you find the transfer function for me? in less than 1 minute. Can you do that? Using the trick I just told you earlier, replacing C with 1 over SC, right? Replacing L with SL, and the rest is the same. Can you find this the transfer function of this circuit? So once we do this, 1 over S, we got 1 over SC here, and we got SL here, we got R here, and we got VIS here, and we got VCS here, right? So we can write VC in terms of VI using voltage divider. Okay, again. By using voltage divider, we found that VC is equal to 1 over SC divided by 1 over SC plus R plus SL times VIS. This is voltage divider, right? Hope you remember. And so it is actually very easy because the transfer function is VCS, right, over VIS, and that is equal to 1 over S squared LC plus SRC plus 1. And that is 1 over LC divided by S squared plus R over L S plus 1 over LC. So this is the transfer function of this circuit. This is a transfer function of this circuit. So what it means is that if we know this transfer function, and we know if given any input signal, we can find the output signal from this circuit, right? For example, if the input signal is the unit step function, then you could multiply it by 1 over S, and then take the inverse Laplace transform, and you're going to get the output signal. Or if the input signal is the impulse function, then you multiply it by 1, and you're going to get the output signal. Or if the input signal is a unit ramp, if the input signal to the circuit, for example, if this guy is a unit ramp, then you just multiply the transfer function by 1 over S squared, right? And you take the inverse Laplace transform, and you're going to get the voltage across the capacitor. Given that the circuit doesn't have initial states, given that at time 0, the voltage across C is 0 and the current in the inductor is also 0. That is what the zero state response means. Okay? Now, give me just 3 more minutes to tell you the last property. The last one, the previous one, time convolution was the 6th property. So the 7th property, okay, is called the time periodicity. Time periodicity. This is probably, it might be useful, but I doubt it. Time periodicity property. If xt is periodic with period t0, then the Laplace transform of xt ut, okay, is equal to 1 over 1 minus e to the negative st0 and then xts, sorry. Where x1s is this is time periodicity. So when you look at it, it may look complicated. Okay, it may look so difficult, but please take a look at this example. You'll see exactly what this means. Okay, so let's look at this example. Suppose we are given this periodic signal, right? And it starts at time 0. Okay, and this signal is a square wave, a rectangular pulse signal, rectangular pulse train. This is what we call it, rectangular pulse train. And it goes on forever, but it starts at time 0. Okay, the signal starts at time 0, rectangular pulse train. And let's suppose that the height is 1, and this is d, this is t0. Now I want to find the Laplace transform of this signal. Now, if we try to do it direct method, right? If we try to do the integration, plug into the definition for Laplace transform, you'll find that it is very complicated, almost intractable. Okay, but we're going to use this property to find the Laplace transform. So, what this means is that the first thing to notice is that we multiply it by u. Okay, we multiply it by u to indicate that the signal starts at time 0. We're only interested in the signal that starts at time 0. So in this case, it fits perfectly. We don't have to do anything. So in this case, we could drop the u here. All right. And now the next thing is to find this integration. So if you look at this integration, it integrates from 0 to t0. It integrates from 0 to t0, right? So what it means is that we're just trying to find the Laplace transform. This is the Laplace transform of the signal x in one period only. We're taking the Laplace transform of x in just one period. So no matter what x is, we cut it one period out of it, and we pull it out. We're only interested in just one period. We take the Laplace transform of this signal only. Okay, we don't care about the rest, just one period. We take the Laplace transform of this signal and then we plug it into here, and that's it. All right, so let's do it. So x1. So x1s is just is the Laplace transform of give me one minute. I know you're hungry. Okay. Right. This is what x means. This is what x1 means. The Laplace transform of this guy. Right? So what is the Laplace transform of this guy? This is just ut minus d, right? Okay, and we know that the Laplace transform of ut, right, is 1 over s. What about the Laplace transform of ut minus d? We could use the time shift, right, to get e to the negative sd times 1 over s. This is from time shift. Okay, and so we have 1 minus e to the negative sd over s, right? So we can use the time periodicity property to get x equal to 1 over e to the negative sd over 1 minus e to the negative st0 times 1 over s. And that is the solution. Okay, easy, right? I think the hardest part is to figure this one out. That is the hardest part. Once you get past that, it's okay. It's gonna be easy. Okay, sorry for the late, 5 minutes late, and see you next Tuesday. Oh, attendance. Oh yeah, very important. Sorry. Sorry that you have to remind me every time. So sorry. Which one do you prefer today? A, B, C, or D? What? A C, right? A cat. Yeah, I know you like cats. A cat. C cat. C cat. F? You want F? No. Hope not. Oh, you want an A? No, a C cat. C cat's okay. Okay. C cat. Mark it as a C cat. C. Oh, yeah, I have to stop recording.